A very good afternoon, everyone. This is Arun Sharma from MIDAS. Today I'll be talking about the nonlinear time history analysis using seismic isolators. So as you can see in this bridge, I've tried to zoom in at the location where we actually have the lead rubber bearings, which will possess nonlinear properties, and we'll be able to perform a nonlinear time history analysis. Since our focus is on nonlinear time history analysis using seismic base isolators, we will not dwell into the modeling of this bridge. So I'll open a ready-made file. I mean, the bridge geometry will already be there, and then I'll start defining the properties for lead rubber bearing. I'll define two types of lead rubber bearing. LRBA, that is for abutments, and LRBP, that is for piers. After that, we'll create nonlinear links at bearing locations. We'll convert loads to masses for taking into account the inertial effect of the structure, and then we'll enter the analysis conditions for nonlinear time history analysis. In this, we'll apply two types of time history load cases, which will have a time varying static load. That means the self-weight and the superimposed dead loads are pooled together in a dead load case, and we'll apply this through a time varying static load. I'll explain more about it in detail a little later on. Then we'll apply ground acceleration for simulating the earthquake effect along the global X and Y direction. After that, we'll perform the nonlinear time history analysis and quickly go through some results. So this is the overview of the bridge that we'll be working on. So as you can see, it's a 3-span steel box girder bridge, and we'll have two abutments. So the two lead rubber bearings A will be applied at the abutment locations, and the lead rubber bearing P, which is for the pier, will be applied at the two pier locations. These are the properties for the nonlinear links that you can see here. I'll be entering these values shortly, but before this, let me explain you the degrees of freedom and their notations. Let's say there are two nodes N1 and N2, and we connect from N1 to N2. Then the connecting direction becomes the local x-axis for the link. Now perpendicular to perpendicular to this x-axis, we have the local y-axis, and orthogonally we have local z-axis. So all the degrees of freedom and the stiffness for along these axes are applied in terms of the local axis system, which is just defined based on how you connect the two nodes. So when we say SDZ, it is this direction, SDY and SDX are the given directions. I'll apply general links to model the lead rubber bearing, and I'll take this thing in little more detail right now. So there are two ways of applying general links in MIDAS. The first type being element type, under which the link element directly reflects the nonlinear behavior of the element by renewing the element stiffness matrix in the process of analysis. Or in simple words, when you do the analysis, the stiffness matrix of that element is modified during the analysis. if you choose element type. But if you have created the link as force type, then what program does is the force type general link element does not renew the element stiffness matrix. It reflects the nonlinear behavior indirectly by converting the member force calculated on the basis of nonlinear properties into an external force. Or in simple words, when you apply force type general link, then what program does is it calculates the forces that are being developed in that link element based on the nonlinear material properties or nonlinear properties that you have applied, and then converts those forces into external force and apply to the structure. So basically the stiffness matrix is not modified in this, and the forces are calculated based on the nonlinear properties during the analysis and then converted at each and every step into external load and applied to the structure. So it's just like action and reaction. And talking about lead rubber bearing isolators, so what are these and how they are interpreted in the software? So lead rubber bearing isolators retain the properties of coupled biaxial plasticity for the two shear deformations. That means if you look at the global plane X and Y, and the properties of independent linear elastic links for the remaining four deformations. That means for dx and dy in the global, in the global plane X and Y axis, the shear the shear components are coupled, just like a lead rubber bearing pad, whereas all the other four deformations are are linear elastic springs for the deformations. And along with adding these the stiffness for for these degrees of freedom, you can also go ahead and add a linear viscosity damping coefficient if need be, which will be entered as in parallel to the springs for each direction. So then what are the parameters we require for entering a lead rubber bearing isolator? We need the stiffness, which is the initial elastic spring stiffness before yielding, yield strength, that what force, after what force will this spring yield, and then post yield stiffness ratio, that is the ratio between the post yield stiffness to the elastic stiffness prior to yielding. We'll also the lead rubber bearing goes through a hysteretic loop, and there are parameters alpha and beta which we enter to compute the behavior, observe the behavior during such excitations. So all these parameters will become more clear once we start modeling and entering these properties in real time. So what I'll do is go ahead into the program itself and start modeling. So let me open the structural model, which already has and all the things defined, the geometry, the support conditions, the loading data is already there. Let me switch on the hidden view so that you can see there are two box girders. If I press down the control button from the keyboard and hold down my wheel mouse button, I can rotate the structure freely about 360 degrees, and you can see there are two box girders kept adjacent to each other, and there is a cross beam connecting them, and on top of this you can have your deck, or you can go ahead with grillage analysis. I'll not dwell much into how the geometry was generated. It's fairly simple geometry, as you can see, and we have a single column pier with a pier cap on top, and where we want to create the bearings we have two nodes displayed. Now let me display the supports to you. I'll right click on the supports and select display. So you can see at the bottom, if I zoom in further, you can see there are two nodes where actually the bearing will be applied. and the base of the bearing is kept fixed by applying a fixed support, and the center line of that girder is connected to the top of the bearing through a rigid link. And if you want to see that, I can just right click and display on the screen as shown here. And display everything. So now let's proceed by defining the lead rubber bearing properties. So I'll right click on the model view window, go to boundaries and select general link properties, then click add and then enter the name as LRBA for abutment. Again, as I mentioned, there are two types of general links you can consider, element type or force type. So I have chosen force type because under force we have certain different type of base isolators, bearing isolators or dampers already defined. So you can choose a viscoelastic, gap, hook, hysteretic system, lead rubber bearing isolator or friction pendulum system isolator. So I chose lead rubber bearing isolator, and then I can enter some self weight if I want to consider its weight and mass, but for the time being I'll ignore this. I'll move on to define linear and non-linear properties. In general link there are always two sets of properties. Linear properties kick in during the linear analysis, and the non-linear properties kick in during the non-linear analysis in conjunction to the linear properties. But the units are here ton force per meter. Let me change the units to kips and inches so that you can have some idea about the magnitude. Kips and inch. Then right click, boundaries, general link properties, click add, enter the name as LRBA lead rubber bearing isolator. So I'll apply the stiffness along X, Y and Z. X being the vertical axis, I'll apply very high stiffness of 26828.353 in dy and the z direction, which are the global x and y direction, as I showed you in the previous slide, is 18.82. I'll allow the rubber pad to move, so therefore I'm applying relatively lower stiffness in these directions. I'm not defining any damping here, so I'll leave them as 0. And for non-linear properties, I'll apply them again in two axes, dx and dz. For this, we have the non-linear parameters that we need to enter. So stiffness being the stiffness of the initial stiffness of the spring that we want to have. So this will be 61.54. Then yield strength will be 34.59. The post yield stiffness ratio will be 0.08917. Hysteretic loop parameter alpha and beta will be 0.1 and 0.1. What you need to consider or keep in mind is their summation of the mod values is always equal to 1, and all the abbreviations or symbols that you see here have been shown, and the mathematical formulation of the function generation have been described here. And more information can be available or looked after if you just click on or just hit F1 from your keyboard. It will directly take you to the online help page where it can show you the details about defining general link properties for lead rubber bearings. Then you can click OK, and then similarly I'll define for DZ direction, again Z being the local axis, so which happens to be the longitudinal direction, and I'll enter the value as same as previous one, 61.54, 34.59, 0.08917, 0.5, and then click OK, and then click apply. So we've defined one property for abutment. Similarly, we'll define one for pier. Everything else remains same, just the stiffness will be modified. Vertical direction is 72180.64, 39.32, 39.32, this value will be 123.42, yield strength becoming 74.14, ratio becoming 0.0862, 0.5, and then click OK. Similarly, one more time for SDZ, or DZ direction, stiffness value will be 123.42, 74.14, 0.0862, 0.5, and then click OK. So this is how we have generated two types of lead rubber bearing isolator. Then we'll click close here, and now go ahead and apply them as links onto the structure. For this, let me switch to the wireframe geometry so that I can just see the center line, and clearly I can scroll forward and zoom in at the nodes where I want to create the links. So right click, go to boundaries and select general link, and then you can select LRBA, click on the two nodes, and then just click on the top node and then the bottom node. Go on and create top and bottom. The moment you do this, you can see X, Y, and Z. So the properties will be applied in this direction. Now I'll press down my wheel mouse button and just drag my mouse to comfortably pan the structure while maintaining the same zoom. I'll change the property name from LRBA to LRBP for pier, and then click on the top node and the bottom node, top node and the bottom node. If you wish, I can zoom forward and you can see it more clearly here. Let me zoom out and come to the next pier. And then finally for the last abutment, I'll change the property back to LRBA. Clicking on the nodes again, 1, 2, and 1, 2. Then click close. If you notice, I need not remember the node numbers at all in MIDAS Civil. I just clicked on the nodes and the program automatically registered the node numbers and created the links. So this is how comfortable MIDAS Civil is to play around with. Now once we have defined the links, now we can go ahead and define the time history functions. So for that, let me right click, go into load, and go ahead and define time history analysis data. So for this, we'll first define time forcing functions and then click add time function. But before that, let me go into the bring back this slide and talk about what are time history or the time varying function time varying static load functions. So what happens is, unlike linear analysis, the principle of superposition does not apply to nonlinear analysis. So since this in this example we have both dead loads and seismic loads, linearly combining the separate results due to each load afterwards is incorrect. So as we all know, in nonlinear analysis, we cannot use the principle of superposition and just add the uh, results that are coming from linear analysis in order to see the complete picture. So for performing a time history analysis, we need to consider both loads acting simultaneously, and in order to reflect the dead loads in time history analysis, the time varying static loads function is used. So to those for those engineers who are relatively new to time history analysis and the jargons, I'm just making this more lucid and clear that time varying static load, as the name suggests, is a static load which is applied over a given time period so that its effect can be clubbed together with the nonlinear time history analysis. So this is what we have for including or considering this kind of effects, so that we can take into account both loads, that is the dead load that is acting on the structure and the seismic load in the same time. So continuing, this function basically creates a condition in which dead load is in place at the time of performing time history analysis for seismic loads. So I think this last statement makes the entire definition a lot more clear. So when there is a seismic event, the dead load is already there onto the structure. So if you want to simulate such a condition and do a nonlinear time history analysis, then you got to use time varying static load function. Now I'll show you how we'll use this function. So I'll click on add time function and then just define a function. I can use any name for this. Ramp I'm using just because I'll create a ramp of loading, and type of time function data type can be normalized, acceleration, force or moment, or normal. Since it's a user defined function and it is bound to be used for time varying static loads, you ought to select normal type, and then you can enter time as for 0 seconds 0 value. For let's say 2.5 seconds it attains the full value, and at 5 seconds it's also at 1. So you can see there is a ramp of loading, and till 2.5 seconds the loading that you will be applying will reach from 0 to its full value, and thereafter it will stay as the full loading onto the structure. So this is the ramp function that we have defined. I'll click OK here. Now I'll also define the earthquake loading. So let me click on earthquake here, and you can see from this drop down arrow or menu, there are more than 50 built-in earthquake records that you can use from. They are predefined set of major earthquakes. So I'll click on 1940 El Centro site for 270 degrees. For every site you'll see 3 records along the x-axis, along the y-axis, and along the z-axis. So this 270 degrees basically represents your y-axis. You can click OK and you can see the earthquake acceleration graph. I'll click apply and add for the same site. I'll use 180 degrees for the x direction. I'll click OK and again click OK to consider it. But let's say you want to create a earthquake response spectrum from this given acceleration. So you can just click on this button, and then you can include the damping ratio if you want to have, let's say 0.05, and then you can click generate. So the program will generate for this earthquake acceleration what is your response spectrum. So we have such enhanced capabilities which can be used by the engineers as and when needed. Then I'll click OK and stick with the normalized acceleration graphs for the two earthquake events. Then I'll click close here. Now I'll right click again, go to loads and go to time history load analysis data, and now define time history load cases. So I'll click add here and enter a name. So I'll define two load cases as I mentioned previously. One is dead load and other will be earthquake. So I created this by name dead load, and analysis type will be nonlinear. Analysis method will be modal, and time history type will be transient because it's not periodic. Since we are using modal analysis, we will be applying eigenvalue analysis control also, so that we can have the eigenvalue analysis and get the mode shapes from there. The end time will be 5 seconds because if you remember, we have created the ramp function for 5 seconds. Time increment is a very crucial input for and it's a very crucial input, and it determines the accuracy of your time history analysis. So and this value can be assessed as a thumb rule as 1/10 of the minimum of the two, and those two values are either the total time of the loading that you have applied, I mean the period of the function that you have applied, not the end time but the period of the function that you have applied, or the natural period of the natural frequency of the structure that you are assessing. So for this structure, the natural frequency was 0.02, or the period was 0.02 seconds. So we divide that by 10, which turns out to be 0.02 seconds. Sorry, 0.002 seconds. So basically you need to see which of these two values is lower, and then use that for time increment. So either 1/10 of the period of the function that you have applied, or 1/10 of the natural period of the structure. And increment and the step number increment for output. This means that after how many steps the program should register or report the result for the output. So I'll choose this as 5. So basically 5 multiplied by 0.002 seconds will mean 0.01 second. So for a duration of 5 seconds, from 0 to 5 seconds, the program will report the result for every 0.01 second. Alright. So these are the controlling parameters for this load case. And then damping method is model, and the damping ratio, since we are applying a static load case or time varying static load, I want the structure to be quickly damped, or there should be no unbalanced oscillations. So, and it should lead to a quick convergence. So I'm entering a damping ratio of 0.99 or 99%. Then I'll click apply, and in this manner I have defined a load time history load case for dead load. Now I'll change the name to earthquake. It will be nonlinear model transient. The end time will be 50. The increment time increment will remain as it is. The number of step number increment for output will remain as it is. Then here is the dialog box where you can control the sequential loading. So you want this earthquake time history load case to be applied subsequent to the load case for that you just defined. That is, so TH stands for time history, ST stands for static load. So you just defined a time history load case for dead loads. So you will just select that. So what the program will do, it will first apply time history dead load case, get its result, then you can choose to accumulate the displacement, velocity and acceleration results from this analysis and use this as the initial condition for your earthquake simulation. And whatever is the final step load for the time history dead load case will remain as constant for the earthquake time history load case. So this means from by the end of time history dead load case, whatever load is on the structure, that means till 5 seconds, when the structure has when the complete static load has been simulated onto the structure, it will remain as constant dead load onto the structure, and then the program will start applying this earthquake time history load case. So basically this will determine the initial condition of the structure prior to this earthquake event, and the results that you'll see for this earthquake time history load case will be having the cumulative effect of the initial loading case, that is the self-weight onto the structure, and the earthquake excitation put together. So in this manner you can add or combine the two different load cases in for nonlinear time history analysis. Had this been linear, then the linear superposition will still work, but for nonlinear analysis, this is the way you should do it. The damping will be modeled, but the damping ratio I'll set it as 0.05 and then click OK. So you can see this is updated in the dialog box here. Now I'll click on eigenvalue analysis control and then go for Ritz vectors and specify for each and every load case how many frequencies or mode the program should consider. So one for dead, for ground acceleration along x-axis, let it be 8, click add, and for y let it be 8 and click add. So basically in total 17 mode shapes will be considered in the analysis. Then I can click OK here and then click close. So since we are performing eigenvalue analysis, we need to convert self-weight and other nodal loads into masses. So I'll go to model and click on structure type, and there we have the option to convert self-weight into masses and convert to x, y and z direction, and then click OK. So in this way you can convert the self-weight into masses. Now you can go ahead and convert nodal loads into masses. So you can go to masses and click on loads to masses, and then you can select dead load with a scale factor of 1, should be converted from just being load to masses, and consider the inertial effect and then click OK. So the moment you do that, wherever you applied a nodal load has been shown through this symbol, which means that loads are converted to masses for analysis. Now having done this, we can go ahead and apply this time history loading onto the structure. For this, we'll tell the program, so we have defined the time forcing functions, we have defined the time history load cases, but now how they should be applied to the structure is remaining. So we'll first come to ground acceleration, where we'll select the earthquake load case that we defined. That is, this is how the load should be applied to the structure. So this will govern the application. The function will govern which function or the which time function should be applied along which axis. So I'll select it, the Lcent t for x-axis, for y Lcent h. You can also consider for direction direction z. And along with this, you can also set the arrival time of these functions. So if you want, there should be a lag between the vibrations for the two directions. You can choose to add some time interval between them. If you want to increase the scale of one of the vibrations or in one direction, you can choose to do that as well. And let's say the structure is not aligned orthogonally or along the global x and y directions, and your earthquake is in the global xy direction, or let's say the structure like this is in the xy direction, but your earthquake acceleration is traveling at, or should be applied at a certain angle, let's say 30 degrees with x-axis. So you can choose to do that also by entering the angle of horizontal ground acceleration with respect to global x-axis. But for the time being, I'll stick with the by assuming the direction of the earthquake and the global x direction are in the same direction, so the angle will be 0. Then I can click add here and click close. So which function, how it should be applied and when it should be applied has been defined. And now we'll define under time history analysis data how the static load should be applied, that is the time varying static load. So here I'll select the load case as dead load, the static load that we define as a dead load, which will include the self weight and the superimposed dead load, and then the function, that is how it should be applied. So this is through the function ramp that we define, and then click add and then click close. So in this manner we have completed the definition of the time history load cases onto the structure, and now what I'll do is just click on perform analysis and bring up the model view window so that you can see the iterations that are being performed for the nonlinear analysis, and in the end it will show you the analysis runtime. And since I'm running this analysis during the live demo session, you can assume that it will not take longer. And here we are, it took about 20 seconds for this analysis. So you can appreciate the speed of analysis in MIDAS Civil. Let me auto hide the message window, and now let's quickly see some results. So I'll right click and go to time history results, and there we can have results displayed in several different ways. We can either have the tables and results generated in contour format for displacement, force for beam, truss and general link member, or we can have the force diagram for them. We can have the stress diagram for beam or truss but not for general link. We can have time history graph or time history text reports. So what I'll do is start with time history graph and click define or modify function, and here I can specify what kind of graph I want to create. I want to create a graph for general link deformation or force, and click add new function, and here I'll enter the name as let's say nonlinear link number. You can display the number of the links on the screen also. For this you can go to display and select general link number and click OK, and now you can zoom in and choose which link you want to select. So let's say I want to display or create a function for link number 4. So I'll select link number 4, and this graph should be for shear y, sorry, small y, and then from here I can select the link which is link number 4. And now as you can recall, we went from top to bottom, so that is the top node is ith end, the bottom node is jth end. So I want to see the shear at the base of this lead rubber bearing, so I'll click on j node force, and then I'll select the component as fy, and I want to see the results due to earthquake load case that we defined, which will have the cumulative effect of the dead load that we applied and thereafter the earthquake being applied. Then I'll click apply, Now I'll define one more function for the same lead rubber bearing, but this time I'll have displacement about the local y of the member, that will be the global y direction. So I'll choose the link as same link number 4, and deformations along local y direction dy, which happens to be the global y also, and then click OK. So I've defined two functions. I click back, and now what I'll do is select which function should come on the y-axis and which one should come on the x-axis. So I want the shear value to come on the vertical axis, so I'll click add from the list. On the horizontal axis, it can either be against time, or it can either be against any other function that you have defined. So I want to have displacement on the x-axis. You can give some title if you want, or I'll just say LRB4. You can choose how many decimal points you want to have on x and y axis. You can even choose to have the exponential representation, and then you can see it should be a time history type of graph. Then click on graph, and this is what program generates. So as you can see, this is the hysteretic loop, or the hysteretic function the lead rubber bearing has gone through. And this is just a reminder, this is basically the shear at the base of the lead rubber bearing in y direction against the displacement along y direction. So you can see when the displacement is increasing, and what's its relation with the shear, and how the cyclic hysteretic loop has been formed based on the parameters that we defined under the nonlinear properties. So this is how you can generate hysteretic curves. Now let me go ahead and define some other simple function. Let's say displacement, velocity, acceleration. I'll click add new. I want to see what is the pier top displacement under this earthquake simulation. So I'll enter the name as, let's say, pier displacement for pier top. I don't know the node number, but I know this is the pier top here, so I'll just click here and the program will read the node number as 77. Then the type of result I want to see is displacement. The reference point can be ground, can be along with ground motion, and can be any other node. So this is also some useful feature with MIDAS Civil, where you can choose the displacement graph to be generated with respect to ground. You can choose to add the ground acceleration to this displacement so that you can see what is the permanent displacement in the structure along with the ground. Or if you can choose with this, the displacement of the particular node with respect to a particular node, so you can specify the another node and see the displacement with respect to that node. The component you can see is dx. Let's say you can choose dx, dy, dz, rx, ry, rz. I'll stick with just dx and then click OK here, and quickly go back and create the plot for it. So I'll click on displacement pier top, add from the list. I'll remove. You can have multiple functions on the x-axis also, but for now I'll just have one, so I'll delete the nonlinear shear y, and on the horizontal axis I'll have time, and then I'll just click graph to generate the graph here. And this is the pier top displacement during the earthquake excitation. Now let's see the complete picture of earthquake with base isolators and the superstructure, how they interact in real time, and that will be something fun to watch. So what I'll do is, let me simulate the superstructure as solid geometry. then right click, go for time history results, and that I'll go for displacement, velocity and acceleration of the structure. I can choose the load function as earthquake, and let's say I want to see for the x-axis, or let's say for the y-axis, and then you can choose what type of animation or the result you want to see. Let's say displacement dxyz, and I'll click on animate, and here I can set the time interval from what time duration to what time I want to see. So just to save some time, because we'll generate result for quite, it will take a little while to generate this. I have already captured this animation and I'll show it to you, but I want to show you how you can generate uh, animations in the program. So I've set the end time as 10, the increment is 0.1, and start time as 0.01. Then I'll click apply, and before you get scared about the deflections or the deformation, this is a exaggerated image of the display so that you can see the displacement. But if I just check on the legend and then click apply, you'll see that the displacement is just 0.1, 0.02. In the z direction is maximum is minus 1.15 inches. So this is an exaggerated scaled up image with the scale factor being 238 times the actual displacement. So you can see this as exaggerated, so don't worry about it. Let me undisplay the link number, okay, here, and then you can see this is a control, this is a record button which you press, so the program will start creating the recording for this event. And I have just created the end time as 10, so it will go from 0 to 10 seconds and create the movie for it. So while it is generating, I can address a couple of questions that came in while I was doing the presentation. So I have a question from Craig. In the worktree, why was the time varying static load added prior to the ground acceleration? For this I need to go and show it to you. In that, it doesn't matter. Basically, the layout of the worktree doesn't show you the sequence of adding the load case. Alright, so if it is coming prior to the other one, that is just the way it is programmed. So even if you defined the ground acceleration first and then time varying static load, but you are seeing it the other way, it is not going to affect anything. It's just the how the program has been formatted to display it in the worktree. Alright, Craig? So friends, if you have more questions, you can ask me while this animation is being generated. In the meantime, let me find out the files that I just generated before. So this is the recording that I generated from the program itself, and as you can see on this bar, the earthquake acceleration graph is there, and then there is a meter which is moving along the earthquake acceleration, and you can see how the structure is behaving, and you can see the relative displacement coming between the pier cap and the superstructure. They are not moving as a rigid member. So this is a recording for entire 50 seconds, but the time increment step has been chosen as 0.05, and therefore you can see in the reading also it jumps every time 0.05 seconds. So in this manner you can create animations, and I'll show you how you can save them, and once you have them as an AVI file, then you can add it to your presentations, you can add it to your displays, or anywhere you want to share it with the other engineers to show what is exactly happening on the structure. It's also a very good verification tool, as you can see. If the deformations or the movement is not uh, as you expected, then you can probably figure it out that okay, that this bearing or this location is deforming unexpectedly uh, and not as per your expectation, so you can go ahead and verify and modify that. And now you can see, since there are just the earthquake excitation is dying out, so you can see this structure is also trying to restore back to its initial format, but you can appreciate the related displacement between the superstructure and the pier cap. And now you can see here the animation is completed, and it is now playing the recording for 10 seconds at an increment of 0.01, and therefore you can see how gently the structure is moving because of the presence of the lead rubber bearing. So this acceleration was applied in the y direction, so therefore largely the movement is in across the girder. And now I'll tell you how you can save these recordings. So once you created the recording, you can just click on the save button and enter the name, and then just hit save. It will save it as an AVI file. As you can see, I've already saved 3 animations prior to this. And once you are done with this, you can click close to restore back to its initial shape. Then I'll click on initial view. Alright friends, so that was all I wanted to share. I'm getting a couple of more questions. Let me quickly answer a few of them. So MGAD has asked, do you model the deck slab with the steel boxes? Depends. If your structure is not very symmetric, it has curves or skews beyond the grillage limit, then yes, you need to model it with plate elements. But if you, and also if you are doing moving load or live load analysis, then you probably want to do that as well. But if the structure is fairly simple, regular, as you can see on the screen, which is symmetric, you can just remove, instead of adding more members to the structure and increasing size of the stiffness matrix, you can just replace them with the vertical loading onto the structure, and then you can convert that loading into masses and consider the initial effect. Alright, next question we have from Daniel. It is, can you simulate impulsive loading like blast? Not The blast loading and impulsive loading are slightly different. Impact loading is something you can simulate through time history. For example, let me go to the pre-processing mode, right click, go to load, and time history analysis data, then time forcing functions. Then I click and add time function. Here I can define some function, let's say again of normal type, or if you want to have some force associated, and you can add the force function also, but let me choose normal type for now. So what I'll do is 0 seconds it will be 0, 1 second it is 0, then 1.001 second, let it assume its full value, and then 1.0011 it slashes back to 0, and then till 2 seconds let's say it is 0. So now whenever you will apply a static load to this type of function, the function value will be multiplied to the as a scale factor to that loading and will be applied. So if you apply this kind of function, so till 1 second there is nothing, and all of a sudden there will be a peak and it will hit the structure for a given duration of 0.0001 seconds, and then it will disappear. So if you want to have that kind of impact loading, you can control the time variation, you can control uh, the uh, the period, how you want to increase it. It can instead of just being peak like this, it can be made more broader. Let's say for 1.1 seconds or 1.005, it is still 1, and then it comes down from 1.0051 to 0, or let's say 5, let's say 1.01. So basically you can increase the width of this function, let's say 1.3, and then thereafter for till 2 seconds is 0. So you can create these kinds of functions basically, and use them just like ramp. We created similarly. You can create these kinds of any user-defined function and apply it as load onto the as an impact load. But since we say impact load, it is like it touches and it vanishes. So therefore I use such a small peak interval. But blast loading is something the energy dissipates throughout the structure. Alright, so there are the vibrations that are coming, originating from one point and then dissipating through over the structure. So that is little different than the impact loading. You can have it like a collision load, something that you want to simulate, but I would have my reservations, or I would like boil down this thing to simple impulse or impact analysis and not call it if I'm doing it for a blast simulation. So Daniel, does it answer your question? Alright guys, there are a couple of more questions coming in. Thanks Daniel. Since we have 1 more minute, I'll take up one more question. So this question is coming from Brad, and he wants to know, what do you mean by nonlinear analysis indirectly? I see. Okay, for force type maybe. Alright, so okay, as I explained previously, right click, go to boundaries, general link properties, click add. So there are two types of applications. It can be either element type, where you can directly define inelastic hinge properties and tell the program to modify the stiffness matrix as the analysis is being performed. But if you happen to have those numbers right off the top of your head, and you don't want or not even from all these numbers, but if you don't want the stiffness matrix to be modified, let's say for a real lead rubber bearing, it is a constant chunk of rubber whose stiffness will not vary with actual loading that is coming on the structure. So its parameters are pretty fixed, right? So you can go to the contractor or the manufacturer of such bearing pads, get these numbers, punch it in, and what the program will do, based on those nonlinear properties, it will calculate what forces are coming into that lead rubber bearing pad, and how these forces will be transferred from the superstructure to substructure, or from substructure to the superstructure, based on different planes. So just as I mentioned, for lead rubber bearing pads, the global XY direction of the plane is the shear is coupled, whereas other degrees of freedom are relatively or are basically linearly independent. So you need to choose your parameters and the degrees of freedom accordingly when you're modeling that type of lead rubber or that type of um, uh, seismic isolators. And same thing, you can simulate the similar behavior using element and springs using inelastic hinge. This is uh, uh, more deeper way, or more, I would not say accurate, but it will give you more control of defining and going much deeper into the analysis. So it's totally the an engineer's discretion based on what kind of parameters he has and to what stage he wants to take this thing for different. As here you can see there are several hysteresis model available that you can choose from for defining the inelastic hinge properties if you want to model them as elements. So bottom line is there are two sets. One is element type, where the stiffness matrix will be modified as per the loading, and the other is force type, where the stiffness matrix will not be modified, but based on the nonlinear property the forces will be calculated, and then those forces will be applied to the structure as an external force, and both will generate the similar behavior. Alright, Brad, does that answer your question? Great. Uh, Alright, friends, we are just in time, and I'll take on all the other questions that are coming in through emails. I will bring out my contact details here. So if you have any question or any comments or feedbacks, you can share it with me on my